little late night out. I think everyone enjoyed themselves. I only spotted 2 people that were asleep at their table as a result of the travel and the jet lag. Many of you are suffering, so well done for turning up here this morning. So today's keynote is by Rob Mueller. Now Rob has already presented a speech in this same room 2 nights ago as part of the Matthew Finlay Memorial Dinner and Lecture. He's also agreed to give us a keynote for the Off-Earth Mining Forum. Many people know who he is. I'll give a brief introduction and then we can get started. He's a Senior Technology for the Advanced Products Development at NASA Kennedy Space Center in the Exploration and Research Technology Programs Directorate. Co-founder of SwampWorks Innovation Labs and Granular Mechanics and Regolith Operations Lab. So he's got a very long and wide experience in very relevant topics to what we're talking about today. And in a completely different topic to what he discussed the other night, he's going to be talking about 3D printed habitats. Thanks, Rob.
Well, good morning.
Good morning. Good morning.
A light crowd this morning. Hopefully people will filter in. Maybe somebody can go downstairs and ring the bell. I noticed there was a few, maybe 10 people downstairs. So anyhow, thank you for inviting me to present this exciting topic today. This is one of the most exciting projects I've ever worked on. And I think it's right on the leading edge of what NASA is doing and what NASA should be doing. A lot of my funding comes from a group called the Game-Changing Division. And when you name an organization the Game-Changing Division, you better be game-changing. And so that's the challenge. Of course, with limited budgets, there's always decisions to be made. And so this particular project is very interesting. I hope you'll find it interesting technically, but also please note the organizational finesse that went into pulling all this work together. So let's get into it. We've already heard the introduction. I am in the SwampWorks, which is an innovation environment. I also like to say it's a way of life. You get up in the morning, you love to go to work, and you're doing something that's never been done before. You're innovating. And that's what drives me in my profession. First thing is shelter. When we go into space, as humans, we need shelter. Humans evolved inside the magnetosphere of the Earth in an atmosphere in a fairly small range of temperatures. So we evolved for a certain environment. When you take that human out of that environment into a new environment, it becomes a challenge. Now that doesn't mean it's impossible. People live in extreme environments on Earth all the time and they thrive. So there's no reason you can't thrive in space, because we have the resources in space. If you have resources and energy just in abundance, then why shouldn't you thrive? But you do have to take care of a few things. So when you're on the moon, the temperature swings radically from about 125 C plus to minus 130 C, depending on where you are on the moon. So it's an extreme thermal swing. The lunar day is 14 Earth days and the lunar night is 14 Earth nights. So it's a long lunar night. You have to survive the lunar night when it gets very cold. So you need thermal protection. You also need radiation protection. There's 2 types of radiation that are of concern: solar particle events, which come from solar flares from the sun, our sun, and then galactic cosmic rays, which are higher energy particles coming in omnidirectionally from the universe, so they come in from all directions. Fortunately, if you're on the surface of the moon, 180 degrees is blocked by the moon itself, so you've cut the radiation down to half right away. So that's good news. If you park your shelter next to a cliff, potentially you could cut it down by half again. If you go into a canyon, potentially you can cut it down again with a canyon effect. And if you find a nice lava tube, then you're good to go. So there are solutions. We just have to think about them and work the problem. There's also micrometeoroids still impinging on the moon today. People that watch the moon on a regular basis, professionals and amateurs, they see these strikes, even today on the moon, regular basis. There are micrometeoroids on the moon. There's also moonquakes. There are moonquakes, tremors, even today. So that's another issue in construction on the moon. And finally, if you land on the moon, this graphic of a lander here, there's a misconception from the Apollo days that landing on the moon is not an issue. However, it is an issue because the landers were small that landed on the moon. And they landed in the mare. The mare had highly compacted soil, about 1.8 grams per cubic centimeter. So it wasn't a problem for Apollo or for Surveyor before Apollo, but they're relatively small vehicles. When these vehicles land, they eject particles at about 5 degrees, 3 to 5 degrees off of the horizontal at 2,000 meters per second velocity. So you're being sandblasted by small sharp particles about 100 microns in diameter, like crushed glass, and you're shooting it at your surrounding environment at 200 meters per second. A speeding bullet is 50 meters per second. So 4 times faster than a speeding bullet, and that's what you're doing to the surrounding environment. If you have your habitat parked right next to the landing pad, you're asking for trouble. You'll be sandblasting your habitat every time you land. So that implies you have to come up with some kind of solution for the landing ejecta. And the ejecta, it actually, the velocity is enough to go into orbit. So when you land, you actually have to tell mission control and all your other entities or nations that are in orbit around the moon that you're going to land because you might sandblast something that's on orbit. It only goes around once and then it impacts again into the surface. But that one orbit of the blast ejecta could damage an orbiting spacecraft. So these are all non-obvious issues. And in fact, we wrote a document in 2011 when the Google X Prize started. We were concerned because in the Google X Prize rules, they give you extra points to land near the Apollo sites, extra points to damage Apollo. So a big red flag went up in our office and we said we had to do something about this, and we got together with NASA headquarters. We wrote a document. It's a non-binding document. It's a set of guidelines that NASA issued. We hope to shame the Google competitors into observing those guidelines. It would be a very shameful thing to destroy Apollo 11 evidence if you landed right next to it. I think that company would not survive. And so we did issue these guidelines. So anyway, there are issues on landing. Let's get into shelter. So I put this in for Serkan because he knows this has already been done in Turkey, and this is ancient, and this is shelter. And it's really amazing. Look at the size of this chamber here. They're living well. They're not just surviving, they're living well. This is a big Manhattan apartment, you know, it's good. And so there's also a community. It looks like a nice community. It looks like a place that I'd like to live there. So these are some solutions for shelter that we have on Earth for humans. This is what we call subtractive manufacturing. They have subtracted material and burrowed into the hillside to make these caves, and that's one solution. Another solution is additive manufacturing, where you add material. This is a clever design by Nader Khalili, and what they do is they fill up sandbags, and the advantage of this construction method is 2 people could do this. You could get your family, tell your kids to fill the sandbags, and a few weeks later you have a house. Now that's ISRU. That's ISRU at its best. So that's why I like this design. After this, you might put some Adobe on it and seal it. Now what's really cool about Adobe is it's a self-healing material. When it rains, all the cracks fill in again. The Adobe heals itself. That's why Adobe is such an ancient material. It works, especially in dry environments. Only in dry environments, actually. However, if you're going to be in space, you're living in a pressure vessel. The pressure we have on station is International Space Station is 14.7 psi. You could have it as low as 10 psi. 10 psi is the pressure that you experience in Denver, Mile High City, right? So pressure is 10 psi. And people seem okay. Some of our conference attendees, they look okay. They look pretty healthy, and they live in Denver. So it's possible, 10 psi. But it's still 10 psi pressure vessel in a vacuum. The moon is a hard vacuum. So you're going to need, in a pressure vessel, any sharp corner is a stress concentration, which is a bad thing. It means you have to put more material on it to make it stronger, and it's a potential failure point. So you really want rounded structures. This is an architectural concept by Roger Dean, who's the famous artist that did the Yes logo. It's a rock band from the 70s. For any of you that weren't born in that period, Google it. But this is a very interesting artist. He's a visionary, and he's actually built this house. This is what it looks like on the inside. Again, it's a beautiful place to live. So we can't forget the psychology of it. Not only do we need good engineering structures, we need places where we would like to live, where we can function as humans. So let's talk about materials. What is basalt? Basalt is an igneous material that comes from lava. And lava is igneous, it means it comes from the center of the earth, from molten rock. Molten rock is ejected or flows out of a volcano or a fissure, and then if the material cools rapidly, then the crystals are small and you get basalt rock. If it cools slowly, then the crystals are larger and you get granite. You make kitchen countertops out of that. So this is a material that is widely found throughout the solar system and on Earth. So that's an opportunity. The Romans used basalt extensively. The Romans invented concrete. The Roman concrete was so good, they put themselves out of business. After the Roman Empire fell, they forgot the recipe. And all the structures they built were so good, they didn't need to be repaired very often. And the Roman concrete recipe was lost. Recently, a university reformulated it based on analysis of these old structures. Basalt is a very good building material. This is proven on Earth, so why shouldn't we use it in space? Another benefit of basalt is it's widely found on the moon, especially in the mare. And not only is it found on the moon, Mother Nature has crushed it for us. Over 4.5 billion years, high energy impact events from meteorites and comets have crushed the rock on the surface of the moon and distributed it over the surface of the moon in a process that the geologists call gardening. And it has ejected in such a way that is fairly uniform across the surface of the moon. It's about 8 to 10 meters deep. So we have a huge opportunity here. We have a large body covered with crushed rock. So on Earth we call that aggregate. You can just scoop it up. It's between 20 and 100 microns. About 80% is between 20 and 100 microns, and 20% is below 20 microns. So it's very dusty. It's a fine dust, but it's a good aggregate. next opportunity we have is this advancement in technology. It's really driven by digital design and digital control of manufacturing machines. You all know what additive manufacturing is, and you know what the common term is 3D printing, but they've done many studies, and this is not only an exciting technology, it's a lucrative technology, and it opens up new possibilities. GE has recognized this. In our lifetime, at least 50% of the engine will be made by additive manufacturing, and at Marshall Space Flight Center, they're already building rocket engine components, and SpaceX is already building rocket engine components that fly on a regular basis. Well, this is here, this is real, it's happening. On a planetary surface such as the Moon or Mars, we will need infrastructure. A lot of people go, infrastructure, what does that mean? So a few years ago, we started a list, and feel free to add to this list. It should get better every year. But it's amazing if you start listing infrastructure that we think we'll need on the Moon to support a base or a settlement. First, you need launch landing pads. Then you need beacons and navigation aids, which will make it safer to land. You need lighting systems. If you want to land in the lunar night or at the poles, the light at the poles is 5 degrees off the horizon. It could blind you. It could blind your sensors. You need lighting systems. You need communications antenna towers. If you drive into a crater, you lose your line of sight RF communications. You've lost contact. So we need antenna towers. Blast protection berms, or orbital assets, but I think antenna towers are cheaper. Blast protection berms for that ejector problem I was telling you about. Perimeter pad access and utility roads. Have you ever driven on a country road? How many hours can you drive on a country road before you say, stop, I want a road? Or call the grader in? It's really tough on your equipment. In mines, the maintenance cycle goes up drastically if your roads aren't maintained. Spacecraft refueling infrastructure. We want reusable spacecraft, not throwaway spacecraft. That means we need a gas station. Radiation thermal micrometeorite shielding, we need all that. Ablative Regolith atmospheric entry heat shields. So we have a project at SwampWorks where we've made a heat shield, an ablative heat shield, out of sintered regolith, and we put it in the ArcJet at Ames Research Center, and it worked very well as an ablative material. So now we can send things back to Earth with heat shields that we make in space. That's quite compelling. Radiation shielding for fission power plants. If you bring a nuclear power plant into space, you need to dig a hole and put it in a hole or put some shielding around it. Otherwise, you have setback distances for humans. Humans can't approach it, so you have to do something about the fission power. You need one very minor detail that pops up when you lay out these bases is you need cabling, you need power distribution. And then you certainly don't want to drive over your cables and damage the cables. And on Mars, Moon is not so bad because of the vacuum. On Mars, there's a passion effect where there's electric discharge. It arcs. In a soft vacuum, these cables arc. So we think you need trenches. You need robots that dig trenches and put the cables into the trenches. Now you can drive wherever you like and the cables are protected. It also means you need less insulation on your cables, which reduces the mass and the weight. Foundations and level. You can't have a good structure without a good foundation. Trenches, one way of shielding a habitat is to dig a trench and then drive into the trench, a large trench, and put a habitat inside the trench. That's the canyon effect. And then you could put a roof over that trench and have shielding. Equipment shelters. Most equipment these days has electronics on it, and electronics will have upset events from all the radiation. So it's a good idea to shield the electronics, but it's also a good idea to shelter the equipment itself because it's in a better environment. So you need maintenance hangars and shelters for equipment. Dust-free zones. We have parking lots for a reason. You don't want to drive your car into a mud field or a dust field and then leave it there, and it's just a mess. So we need these dust-free zones. It will make our operations easier. Anybody know what a thermal wadi is? A wadi is the Arabic name for a dry riverbed. And a thermal wadi is a mass that heats up in the daytime and radiates heat out in the nighttime. So if you want to survive the lunar night, you could warm up a pad, a basalt rock pad, and it has thermal inertia, and then during the night it releases the heat and keeps your equipment alive. Batteries don't do very well in cold temperatures. If you park it on a thermal waddy, now that's a really simple way to keep your equipment alive during the lunar night. Radiation shielding panels for spacecraft. We can make radiation shielding from regolith in space. Regolith mining for oxygen production. 42% of the regolith in the mare is oxygen. If you scoop up 1 kilogram of soil on the moon, you get 420 grams of oxygen. That's pretty good if you want to breathe. So that's a good solution. Water, ice from the shadow craters, and there's even reports now that there's hydroxyls all over the moon. So we still don't know where the water ice is or what form it's in, or if it's hydroxyls or water ice or what. We don't know, but if it's there, we really need it. We need to use it. We've done some work on preparing the landing pads. In my opinion, is one of the first pieces of infrastructure you need, because you land and you want to land safely. And if you can build a landing pad with robotic precursors, then the first time you land, you just land, and then the robots prepare the landing pad, then you put beacons up and lights and all your infrastructure. Second time you land, it's infinitely safer and more reliable and repeatable. So I think we need landing pads. This is a NASA project called the Morpheus lander. It's a oxygen methane demonstration engine with a flash LiDAR autonomous navigation system. So the idea is it flies, demonstrates the propulsion, it blocks methane propulsion, then it lands in a rock field with simulated craters here and simulated rocks here, and then it navigates and it avoids the rocks and craters, avoids the hazards, and lands on the pad. And we've successfully done that at Kennedy Space Center with Johnson Space Center built this lander and operated it. We built this blade for the Chariot. This is the Space Exploration Vehicle is what they call it now. It's an electric rover with active suspension. It's a truck for space. So we're already developing this equipment. And here's a smaller bulldozer type of thing with an astronaut in a standing position. That's where the name Chariot comes from. It's like riding a chariot. We've also been working with Dr. Baruch Kushnevis at Contour Crafting Corporation. He started his career at the University of Southern California. He has over 100 patents in the area of 3D printing concrete. So we have a collaboration with him. He's developed these nozzles. He's extruded this mortar type of cement. It's not quite concrete because it doesn't have large aggregate in it. It's more of a mortar, but it prints very nicely, and he has a trowel, and he can make very accurate objects. So he's had several NASA contracts, and this is a concept of how you could have a robot arm on a rover type of platform, a hex rover, and then you could start building infrastructure using local materials for concrete. You don't want to launch concrete into space. That would be a very inefficient way of doing this. So now you can build hangars, roads, pads, habitats. We just have to develop this technology. Another project we have, the previous work was done by Dr. Kushnevis under a NIAC contract, and I believe he had an SBIR as well. Then we formed a new team 3 years ago, and it was a team of NASA Marshall Space Flight Center, NASA Kennedy Space Center Swamp Works, the U.S. Army Corps of Engineers, Engineering Research and Development Center, Construction Engineering Research Lab. It's the R&D branch of the Army Corps of Engineers. Contour Crafting Corporation and Pisces, Pacific International Center for Exploration Systems, are in Hawaii, and they're sitting on an island made of basalt. So that was a good indigenous material, a good location for us to go do some testing. I'm not going to go in details in here, but we had two sets of objectives. The Army had one set of objectives, and NASA had another set of objectives, but the funding was shared. So we decided to do a joint project and morph the requirements into one set of requirements, but the goal here was to do it on Earth first, build the platform, and then have a different material for space. That was the strategy. The Army wants to fly in with a C-130, unload the equipment, and within 24 hours have a structure standing for soldiers' barracks, and within 48 hours have the soldiers move in. That's their goal. And they do have personnel that can operate these machines, so it doesn't have to be fully autonomous. So they could have a crew of up to 6 soldiers operating these machines. So they would like to build housing for soldiers rapidly using in-situ materials, so they don't have to ship concrete from the United States into the field. And when they say in-situ materials, they mean locally sourced. If you can buy concrete locally, Portland cement concrete locally, they call that an indigenous material because they don't have to transport it from the US to wherever they are. On the NASA side, we have the goal of printing, 3D printing a habitat in space using regolith, using the crushed rock on a planetary surface. So we have all this aggregate, all we have to do is put a binder in it and use robots to 3D print it. That's the basic idea. Of course, NASA has a very rigorous project management structure. We had to have key performance parameters. These key performance parameters, KPPs, the first one was a construction material. State of the art is regular Portland cement, water-based concrete. We can do that. Threshold value is using in-situ regolith materials for manufacturing feedstock using imported binders. So you bring the binders from Earth, but the aggregate is already there. And the goal is to have no imported feedstock materials, everything from your local in-situ planetary surface. Second KPP was in placement. This is a robotic mechanism that drives the print head. Big one. So we're talking about gantry robot. And it has to be mobile. So when you finish one structure, you move it over and print another structure. You can print the whole moon village with one printer. So you have a leveraging. Construction scale. Today we can do 1 meter domes. We want to do pads, foundation pads and landing pads, and curved walls, blast barriers. And then we want to go to full scale. So we want to increase the scale from 1 meter to about maybe 3 meters, 4 or 5 meters high, and about 1,000 square feet. It's about 10 square meters. That's the goal. Printhead construction speed, the big Achilles heel of 3D printing is it's these tiny little layers. It takes forever to build these parts. But in construction, you don't need to be that accurate. I call it a carpenter's measuring tape. If you can be within the accuracy of a carpenter, you're good for construction. That's about 1/8 of an inch. So it's not too bad. First step was building this foundation robotically. We did that. We have a robot here that's provided by the Canadians, ODG, Argo rover, and they provided that to the Pisces team in Hawaii. Kennedy provided the blade, and then we teleoperated this rover to grade the surface. This was a quarry in Hilo, Hawaii, and the quarry was a basalt quarry. So everything you see here is crushed basalt. Then we compacted that graded area with a big roller. The roller is empty, you fill it with regolith, and then it becomes heavy and you compact it. And then we built a payload, a robotic arm with an end effector gripper, and we laid out pavers for the landing pad. And the pavers were made out of local materials. This is a robot we developed at SwampWorks. It's an excavation robot called Razor 2.0, it's the second generation. So we go dig up the regolith, the soil, with this, and then we put it into molds, and we sinter the regolith in the molds. We make these pavers, these puzzle-shaped pieces. Then you lay them out with the robot, and this is what we call the bullseye of the landing pad. That's where the repeated landings happen. If your beacons are good and your landing system's good, you will always land here. If you have an anomaly, you land on the gravel. You don't want to land on the gravel because then you have to re-prep the gravel. It's more maintenance, but it would still be a safe landing. Then we did a hot fire test to see if it would work or not. Next, for the Army, they wanted a system that would automatically dispense all the dry goods. And there's a variety of dry goods. They have gravel, coarse sand, fine sand, and they have some other additives that are different materials that they prefer me not to tell you what they are. But it's just dry goods that make a special concrete mixture. Here you see the dry goods. So what happens is you put the dry goods in these hoppers, and then we have augers. The augers auger the material up into this bin here. We call that the weigh bin. There's 4 load cells underneath the weigh bin. The material goes into the weigh bin, and then another auger in the weigh bin augers it out of this funnel here, this spout, and then the spout goes into a scoop and mix, which I'll show you in a video in a minute. In addition to that, once you put the dry goods into the mixer, the concrete mixer, you need the liquid goods, mostly water, and then some other additives too, some accelerators and different things to enhance the viscosity of the slurry. Then we designed this was a work done by Marshall Space Flight Center, the Army, and Contour Crafting Corporation. We designed a gantry XYZ robot that would position a nozzle, which is here, and now you can print large structures in the envelope of that gantry. Here's the actual gantry in Champaign, Illinois at the Army site. And so you can see this is large. The B-hut they're printing is 32 feet by long, by 16 feet wide, by 8.5 feet tall. Here's a B-hut. They printed it and using regular concrete, and the reason they put a roof on it, we can 3D print the roof too, and then lift it on, or with Portland cement it's hard to do it freeform, but they didn't have the permission to put a 3D printed roof on because nobody could say it was safe. You know, there's liability involved. You put soldiers in here, there's liability. So they weren't willing to put a 3D printed roof on it, but in the future they will. So let's see if I can get this video to work. Okay, help me out. so that build took 21 hours. But they didn't do it. They didn't do it all at one time because shift work, personnel, and so. But the total build took 21 hours, and the goal was 24 hours. So it's in the ballpark. Next up, I'm running out of time, so I'll accelerate here, but I would like to tell you we have a program called the Centennial Challenges program, which was authorized by Congress in 2005, and it's based on things like the Google X Prize, Ortig Prize, the Longitude Prize, yes. And so these historically have shown that if you give prize money, you get much more in return than you give because of the leveraging aspect and the competitive nature of these things. So we have a challenge for 3D printing a habitat, solving the need for safe, secure, and sustainable housing on Earth and beyond. So we want to have solutions for Earth and space. We had the first part was architectural design, 98 entries, 30 finalists. Mission requirements were design a habitat for crew of 4, use in-situ resource, 1,000 square feet habitable space, and you had to have 40 feet cubed dedicated to ECLS, environmental control and life support systems. These were the results, first, second, third place. First one was 3D printing with ice, and so that was a little innovative, and the architects that were judges liked that, and it protects against radiation. The ice is a good radiation shield, so they actually have a spacecraft inside here, and then they 3D print a big shield over the spacecraft. It was an interesting idea. Second place was Foster and Partners, a big architectural firm out of London, and they had a concept where they had inflatables, and then they printed over the inflatables. This actually is the European Space Agency entry, and they use discarded parts of the lander and then recycle those parts, bring a few parts, and then 3D print the rest. So it's a hybrid approach, but very realistic. And phase 2 was phase 1 was the architectural design. Phase 2 was to develop the new material, the material that you 3D print with. And we call it the structural member competition because first they 3D print a truncated cone and cylinder and test that, then they print a beam and test that 3-point bending. Then we have a head-to-head competition, which we just had 3 weeks ago in Peoria, Illinois at the Caterpillar facilities, and they actually had to 3D print a 1.5 meter diameter dome. We had 78 entries. The attrition rate is high in these competitions. 78 teams entered. 7 were able to meet the requirements to qualify to come to Peoria to do the competition, and only 3 showed up. And of those 3, only 2 were able to print. It's not easy. This is our table for materials. We give more points for indigenous materials. The more indigenous it is, the more points you get. Then we have a formula which multiplies the points. Here's the devices or structures that they had to build. 300 millimeter cylinder. These are based on ASTM testing standards. So we run an ASTM standard test on this, and then we know what this is a C78 ASTM test, and this one is C34, I believe. Here's a cylinder being 3D printed with concrete and a robot arm. Here's a beam that has been 3D printed. Here's the beam in a 3-point bending test. These are the 2 points up above and 1 point below. No, it's 2 points below and 2 points above. It's actually a 4-point bending test, I believe. And then this is the interface where it broke, the fracture plane. Here's the dome, 1.5 meters. And 2 teams were able to do it. This is very difficult to do. At this point, right here, you're printing completely sideways, 0 degrees. In 3D printing, anything over 45 degrees or anything less than 45 degrees is impossible. That's why they have all those supports. This was done with 0 supports, freeform 3D printing. It's a breakthrough. Here's the team that did it, They're called Branch Technologies, and they partnered with Foster & Partners, who's the big architectural company. I would like to play this video because I think it's very interesting.
Okay, be quick.
I'm almost done.
Okay.
We are all explorers at heart and share a common goal to seek beyond what we know. Creating a self-sustaining civilization on Mars will bring humanity into the next era, and it is clear that this mission will be the greatest adventure in human history. Fortunately, our collective understanding of Mars grows every day. Our team is expanding our design and fabrication abilities beyond Earth itself. While both Foster & Partners and Branch Technology have been individually focused on innovations in fabrication technology, structural optimization, and material efficiency, the 3D printed Habitat Challenge has provided a platform for collaboration at a new level.
In level 1, we printed a perimeter cylinder of recycled mission materials to contain and amplify the naturally compressive characteristics of local Martian regolith. Because scalability and adaptability are crucial for extraterrestrial habitation, in level 2, we wanted to combine the mission and local materials into one new hybrid polymer that is recyclable, reusable, and adaptable to various printing methods and structural requirements. This hybrid polymer not only performs well under tensile loading, but also allows for an inherently strong and scalable solution that is suitable for constructing a wide range of structures.
Throughout the competition, the team worked very closely with TechMar PM, a materials design company. TechMar is recognized within the 3D printing industry as a design leader in groundbreaking projects. Together, they created a custom material using mission recycled and local indigenous materials per the restraints of the competition.
During level 2 of the competition, we began printing with a plastic that was heavier and required us to redesign the pellet delivery system to achieve the consistency we needed. We relocated components of the system to minimize complications and to increase overall reliability given remote operation.
We investigated a number of geometrical configurations throughout level 2 and into level 3 of the challenge. From bone-inspired structures to regular typologies such as Voronoi and Delano tessellations that are specifically optimized towards the classical M truss that is so prevalent in traditional spanning structures. Furthermore, we utilized a common platform in order to ease collaboration between the digital and the physical realms.
So this competition is about small-scale structural tests. The way that we're approaching 3D printing is to balance both the cost, the weight, and the structural strength. And by using composites and freeform 3D printing with conventional or other materials to provide composite action on assemblies is something that gives a lot of flexibility to the team that is Foster & Partners and Branch Technology.
Too slow. Let me solve this problem. So that's the fanning test. Okay. So in October, we're going to announce the phase 3, $1.4 million prize. It's going to be the large structure, 100 square feet in footprint area, and you're all invited. Anybody wants to form a team, please form a team. Next, I'm almost done, last slide. I think we should 3D print the Sydney Opera House. This would be a great challenge. And it's in Australia, so of course, somebody in Australia already tried it. And this is the Swinburne University of Technology in Victoria, Australia. And they did it with geopolymers and a powder bed 3D printer. Of course, this is tiny, right? It's about desktop scale. So you can see, Australians are already thinking about 3D printing the Sydney Opera House, which is fantastic. But this is my last slide here. Last two slides. Imagine what could be possible. This is where we're headed. I don't know why you're laughing. I don't laugh when I see this. I'm inspired by it. I think this is where we're headed. Those little pictures of burrows, little animal burrows on the moon, I don't think that's our future. I think this is our future. Think about it. This is our future. Freedom for architects. Thank you very much. Yes, that's right. That's right. It takes money.
Yeah, okay, well, one question, because we are way over time. Yeah, they're back there.
I was just interested in how they handle providing tensile strength in these things, like for pressure vessel or something like that.
Okay, thanks for asking. You hit the nail on the head. That's the one missing piece, is the reinforcements. Concrete is only good in compression. Now this stuff that we're using is 10 times better in tension than concrete is. But even concrete is about 4,000 to 6,000 psi in compression. It's about 400 psi in bending. And steel is 60,000 psi in tension. So we need reinforcements. But there are ways of doing it. And that's the next phase, is to add reinforcements to this material and then make it structurally strong enough to build a skyscraper.
All right, so let's keep moving. Thanks very much to Rod for his